Where we left off last time was an example where we're looking at the whole thing is we're looking for area under a curve. We call that the region. But it's more than area under a curve. It's area under a curve above the x-axis between two finite endpoints, A, B. So this is our entire purpose in this. So here's our function, f of x. That's the curve, f of x. It's above the x-axis and within our closed interval AB. This is our area, our region. The way we find this area is by taking small and smaller rectangles within that bound. Here's our function f of x, our x-axis. So that's what we started off. As we saw as well, a couple of things. Well, this area of one of these rectangles is the height and the base, or the width. The height is designated by the function itself, because the function itself gives us the x value. That gives us the height. The width is designated by delta x. And typically, delta x is equal to b minus a over n, where n tells us how many intervals do we want. The bigger n becomes, the more accurate our area becomes. Now, another thing we have, if the curve is not uniform, in other words, if it's increasing or decreasing, we have two things we can calculate. If we go in the left endpoint, in this example, then we get a smaller area that's not the true area under the curve. We call that a lower sum. This is going to be less than or equal to the actual area of the curve. Or we can use the right endpoint. So in this example, since we're using the left endpoints, our input would be a in the first one times delta x plus x1 times delta x plus, so we're always using the left endpoint. And that's going to give us a lower sum of all this stuff. If we use the right endpoint, If we use the right endpoint, then we get too much of the area. We have too much than the actual area. That's called an upper sum. And that's going to be greater than or equal to the actual area. So we have our lower sum is less than equal to the area of the function itself is less than the upper sum. How do we make it more accurate? Make these numbers more accurate if two things occur. One, if we could make delta x, the width of them, make it smaller and smaller and smaller and smaller, then we'll have more accurate, each one of these little rectangles will be more accurate. And in doing so, that means the number of intervals we have will go to infinity. We'll have more and more. So the smaller the interval, the more numbers we'll have. So far, so good. So eventually, our entire goal is where the lower sum is equal to the area is equal to the upper sum. That's our entire goal. So the problem is with delta x. Let's look at the first one. If delta x is uniform, which means the same, then it's no problem. We can easily do that. Just plug and play. But in reality, delta x changes. Between each interval. So the question is now, how do we fix that? And that's what this whole topic's about today. So the first thing we have to do we need a more structured process. Remember, we in our intervals, we start with A and go to B. Where in the interior points that we're looking at, so we have A. That's the first one. Then next to that is x sub 1. The next to that is x sub 2, and x sub 3, and dot, dot, dot. x sub n minus 1, and then that has to be less than b. X sub n, no, let me make that one b. For uniform consistency, we set our beginning and end points. We set the beginning point as x sub 0 dot 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 x sub n minus 1, and we set our end point b, we set that as x sub n. This is b and this is a. So we've just defined each one of our x values in our intervals. So that defines our closed intervals. Remember, each one of these have to be closed intervals. So the first interval is from x sub 0 to x sub 1. The next interval is from x sub 1 to x sub 2. And then so on and so forth. X sub 2 to x sub 3, all the way, blah, blah, blah. So we have those sub intervals for our, these are our delta x's. These are our delta x's. Now, the whole list of these x's, those list of x's are called partitions. The complete list of x sub i's are called the partition P. And it consists of x sub 0, x sub 1, x sub 2, dot, 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 x sub n minus 1, x sub n. It's called partition of our H. Remember, because our first term here was A, our last term here was B. So delta x is how would I define delta x? Width of each subinterval of the closed interval AB. What formula do we normally use for delta x? Very good. B minus A over N. This makes all subintervals uniform. So now we have delta x. Now, next we choose a C sub k value where C sub k is an element of each interval. Why do we need C sub k? But C sub k is an interior point of each of these little subintervals. So this is delta x. It's the interval containing x sub 0, x sub 1. Inside there, I pick a point. That's C sub k. Or in this case, it's C sub 1. Inside the next one, in the next interval between x sub 1, x sub 2, I have C sub 2. And so on and so forth. In the next interval, x sub 2 to x sub 3, I pick another C value, C sub 3. Where the subscript represent which rectangle I'm in. Why do I need those? Because remember, what's the formula for area? Base times height. The height was the function, f of x. And the base is my width, delta x. But we have to define which x value we're going to use. We can choose any x value we want to inside there. So we use C sub k, some value inside there, times delta x. So this will define the area of each of these sub areas. That's A sub k. Now, if we add them up, if we add up all of our A sub k's, we have this equation. Are there any restrictions on what these areas can be? Can they be positive? Can they be negative? Can they be zero? Oops. Crap. Crap, 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 crap. I ruined that. There. Let's call this area 1. If I add up all the areas inside there, is that going to be a positive or negative value? Since it's all below the x-axis, the sum of all these will stay negative. What's the area of that point right there, of that interval? If I had a constant, it's 0. What's the area over here? It's positive. So the areas can be positive, negative, or 0. Because so I had x sub 1 to x sub 2 to x sub 3 to x sub 4. So again, this one's going to be less than 0. This one's going to be greater than 0. This one's going to equal 0. So it's possible to get all those. So we'll call this S sub k. So this formula right here adds up all of those little teeny tiny areas. That's got a name. S sub k is called the Riemann sum. Of f on the closed interval AB. So that formula right there, I'll start on the next page. Because what the Riemann sum talks about is the summation of all these little sub areas. That'll give you an overall area of the curve within your interval, AB. Let's, let's take a little deeper dive into it. So S sub k is equal to the summation of k equals 1 to n of my function at some ck delta x sub k. Now, the reason I put delta x sub k is because now we're going to take it one step further. Up until, if all the delta x's were the same, that b minus a over n, then we'd have all the same. But what really is going to happen is our intervals will not be the same width. In other words, what that says is this. Here's a. Here's x sub 1, x sub 2, x sub 3, x sub 4. Why is this possible? One easy way to look at this is if your data is, if the slope isn't too great, then you can have a wider interval. If it's like in business and sales, if your sales are slow, then it's a very low curve. But then if they shoot up, now we have a lot more in that area. So we got a small interval to have to deal with a lot more data. Okay, so if this happens, our formula is now changed a little bit. We use either the left endpoint or right endpoint values to find the lower and upper sums. In other words, why would it matter which one you choose? If you want to have less than the actual area, then you try to find the lower sum. If you want to find more to be safe, more is safer, at least it's contained in there, then you look for the upper sum. And eventually, as the limit, as they approach both sides, we'll get to the final answer, but that's another story. So, depending on which endpoint we use, for example, let's say our function was x. What if we had that function there? This is f of x equals x. My intervals are defined. Let's say we want the upper sum. So would we use left or right endpoints? Why? Right. Because in this example, in this first interval, we're between x sub 0 and x sub 1. X sub 1 would give me the upper point. So we use upper point, we use the right endpoint on the interval. The left endpoint would give me the lower sum. All right, so far so good? So how will we use this into our formula? The summation as k equals 1 to n of x c sub k delta x sub k. Oh, let me get to this real quick also. If you have non-uniform delta x's, if delta x is non-uniform, then use the which delta x would you use? Now you never think about the pros and cons. Which delta x would you use? Because if all your x's, your delta x's were different size, which delta x would you use for your formula? You use the largest delta x because the largest delta x will be wide enough to include all of your other sub intervals. If you use the smallest one, would this interval fit inside that width? No. But this small interval, if my width is this big, it at least fits in there. I'll have extra, but at least it fit in there. We call that the norm. Oh yeah, I forgot to say. Yeah, you did. So it's norm of the partition P. So the norm of the partition P. What is a partition? It's all of your x values. Because from your x values, you create the subintervals. Now, how do we represent the norm? We represent it like this. Whenever you see the double absolute values around the P, that means it's the norm of P. It's taken the largest value of that um, interval, list of intervals. All right, so let's look at this. We're going to try to get to a more standard value function of S sub k. So S sub k is equal to k from 1 to n. We have to define what is that. what, remember, delta x is b minus a over n. We have to now come up with a formula for the function itself. In our interval, you start at the value a, the lower end, and then we add, or all, since all the delta x is not the same, each one of these are k's. This is k equals 1, k equals 2, k equals 3. So we have k times delta x. So let's go right here. So we have a plus k, delta x is b minus a over n. So our equation, our function, the input will be given by this formula. The function of a plus k b minus a over n times b minus a over n. Because remember, this is for the right interval, because we start off with a, we go to whatever interval we're in, the kth interval of the delta x, or delta x. What this really looks like is k times delta x. And what that's going to do is it's going to give us an interval, a number in this first interval, and then we're going to go to the next one, and then go to the next one, and then go to the next one, depending on what k is. Again, what is this formula called? The Riemann sum. It's the Riemann sum of the function f of x on the closed interval AB. Why is this important? Because we're going to, in next section, we're going to define this further. And that's what we're going to be using from here on out. Let's look at an example. Example 6. Let p equal 0, 0 0.2, 0 0.6, 1, 1.5, and 2. Let P be a partition of the closed interval 0, 2. How many subintervals are there? Why 5? Right. Because basically, let's say the number of partitions. 1, 2, 3, 4, 5, 6. Let's say it's 6. The number of subintervals is always one less than the number of, so it's, since there are 6 of them, it's 5. Yes. The reason being is because the first partition is from 0 to 0.2, and then from 0.2 to 0.6, and then 0.6 to 1, from 1 to 1.5, and then from 1.5 to 2. 1, 2, 3, 4, 5. What is that? So what's that one to be? What's the norm? What's this one called? So what's the norm? Right. Because the first one, it's 0.2 minus 0 is 0.2. 0.6 minus 0.2 is 0.4. 1 minus 0.6 is 0.4. 1.5 minus 1 is 0.5. 2 minus 1.5 is 0.5. This one, the norm, looks for the largest, even though it happens twice. All right. That's the end of section 1. That's introducing us into the concept of